Hello, in this lecture we will prove Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields the relation between the lengths of the sides in the triangle to the length of its CVN. So, in the drawing we have triangle ABC. This is triangle ABC. The length of side AB of triangle ABC is units. The length of side AC equals to B units, and side AC equals to A units in its length. In addition, we know that line segment BD equals to M units in its length. Line segment DC equals to N units in its length, and here the CVN in this triangle ABC is line segment AD. Again, AD is the CVN in triangle ABC, and we know that the length of the CVN is D. So again, I repeat that Stewart's theorem yields a relation between the length of the sides in the triangle, here, CBA, and the length of its CVN, AD, is equal to D units in its length. And according to Stewart's theorem, B squared times M plus C squared times N equals to A. A is the length of side BC. A, we'll open the brackets. Inside the brackets we have D squared. D is the length of the CVN AD. D squared plus M times N. Repeat again. According to Stewart's theorem, B squared M plus C squared N equals to A. We open brackets. Inside the brackets we have D squared plus M times N. So we prove that this equation is true in two different methods. We start with the first method. In the first method, we'll do a construction. That is to say, from the vertex A, we will draw perpendicular on BC. So, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the starting point of the of the perpendicular from point A and BC as E. And we will define the length of this line segment ED as X. And the length of line segment ED equals to X according to our definition. We will define the length of line segment AE as H. That is to say, line segment AE equals to H according to our definition. What is the length of line segment EC? Although it is very easy to see that EC equals to X plus N. So I write it down here that the length of line segment EC equals to X plus N. What is the length line segment BE. From the drawing it is very easy to see that BE equals to BD minus ED. I write it down. BE equals to BD minus ED. That is to say, BE equals to BD equals to M units in its length, and ED equals to X. Therefore, BE equals to M minus X. So write down here that line segment BE equals to M minus X units in its length. In the next step, we'll implement the Pythagoras theorem on the right green triangle. This right green triangle, triangle AED. This again, we implement the Pythagoras theorem on the right green triangle, triangle AED. So, here by PT is abbreviation for Pythagoras theorem, and according to Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. Repeat again, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right green triangle AD, the hypotenuse is AD, and the square of the hypotenuse is AD squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AE squared plus ED squared. I'll repeat again. In the right green triangle AED, according to the Pythagoras theorem, we get that AD squared equals to AE squared plus ED squared. AD equals to D units in its length, therefore AD square is D square, and it is equal to AE square. AE equals to 8 units, therefore AE square is 8 square, plus ED square. ED equals to X according to our definition, therefore ED square is X square. In conclusion, we found out that according to the Pythagoras theorem in the right triangle AD, D square equals to H square plus X square. Okay. In the next step, we will implement Pythagoras theorem in the right triangle AEC. The right triangle AEC. Again, by PT is a relation from Pythagoras theorem. So, in the right triangle AEC, according to Pythagoras theorem, the square of the hypotenuse is AC squared, or the hypotenuse is AC, therefore the square of the hypotenuse is AC squared. And it must be equal to the sum of the sides of the perpendiculars, that is to say, it must be equal to AE squared plus EC squared. So here we created equation number 1, according to the Pythagoras theorem in the right triangle AEC. AC squared equals to AE squared plus EC squared. The hypotenuse AC equals to B units in its length, therefore AC squared is B squared, and it must be equal to AE squared. AE equals to H, therefore AE squared is H squared plus EC squared. EC equals to X percent units in its length, therefore EC squared is X percent squared. So actually we found out that according to the Pythagoras theorem in the right triangle AEC, B squared equals to H squared plus X plus N squared. We will open the brackets of this equation, of this side of equation number 1, and we will get that according to equation number 1, B squared equals to H squared plus X percent squared equals to X squared plus N squared plus 2 times X times N. Okay. In this equation number 1, we have the expression of H squared plus X squared. And we already found out that H squared plus X squared equals to D squared, so we substitute H squared plus X squared in this equation number 1 by D squared. So here B squared equals to H squared plus X, H squared plus X squared, this is actually D squared, plus N squared plus 2 times X times N. Repeat again, according to equation number 1, we found out that B squared equals to D squared plus N squared plus 2 times X times N. In the next step, we will implement the Pythagoras theorem in the right triangle AEB. We will implement the Pythagoras theorem in the right pink triangle AEB. So in the right pink triangle AEB by PT that is to say by Pythagoras theorem, we will get that AB squared, the hypotenuse is AB, so the square of the hypotenuse is AB squared, equals to AE squared plus EB squared, or BE squared. Repeat again. In the pink right triangle AB, according to the Pythagoras theorem, we get that AB squared equals to AE squared plus BE squared. Plus BE squared. Again, AB squared equals to AE squared plus BE squared. The hypotenuse AB equals to 3 units in its length, therefore AB squared is C squared, and it is equal to AE squared. AE is H, therefore A squared is H squared, plus BE squared. BE, we already found out that BE equals to M minus X, yeah. Therefore BE squared equals to M minus X squared. So in conclusion, we found out that according to equation number 2, the right pink triangle AB, C squared equals to H squared plus M minus X squared. We will open the brackets of this side of equation number 2, and we get that according to equation number 2, C squared equals to H squared plus M minus X squared, according to the algebraic identity that A minus B squared equals to A squared plus B squared minus 2 times AB, we get that M minus X squared equals to M squared plus X squared minus 2 times M times X. We have already found out that in equation number 2, we have H squared plus X squared, and we already found out that H squared plus X squared according to this equation equals to D squared. Therefore, we'll substitute D squared in this equation number 2. We substitute H squared plus X squared in this equation number 2 by D squared. And we'll get that here C squared equals to H squared plus X squared equals to D squared plus M squared minus 2 times MX. This is equation number 2. And we have already found out that according to equation number 1, B squared equals to D squared plus N squared plus 2 times XN. In the next step, we create equation number 3 in the following way. We will multiply equation number 1 by m. In the next step, we'll multiply equation number 2 by n, and then we'll add the two equations with each other. This will be equal to equation number 3. So we do it in two steps. In the first step, we'll multiply the right side of equation number 1 by m. This is the right side of equation number 1, so we multiply it by m. So it is m. Inside the brackets we have d squared plus n squared plus 2 times x times n. In the next step, we will multiply the right side of equation number 2 by n. This is the right side of equation number 2, we will multiply it by n. So it is n, inside the brackets we will have d squared plus m squared minus 2 times mx, and it must be equal to the multiplication of the left side of equation number 1 by m. In the left side of equation number 1 we have only b squared, so it is mb squared plus the multiplication of the left side of equation number 2 by n. In the left side of equation number 2 we have only c squared, so it will be nc squared. Okay. So this is equation number 3. In the next step, we'll open the brackets on this side of equation number 3. And we'll get that according to equation number 3, here we'll open here the brackets, m times d squared is md squared plus m times n squared is mn squared plus m times 2xn is 2xmn plus, we'll open the brackets of this expression, so it is n times d squared is nd squared plus n times m squared is nm squared and finally n times minus 2mx is minus 2xmn, and it must be equal to mb squared plus nc squared. So here in this side of equation number 3 we have plus 2xmn minus 2xmn is 0, so those two expressions will get cancelled. What is left from equation number 3 after we cancel the two expressions? Actually, in this side of equation number 3 we have md squared plus mn squared plus nd squared plus nm squared equals to mb squared plus nc squared. So actually this is equation number 3, after we cancel the two expressions. In the next step, we take this square out as a common factor from md square and also from nd square. So what is left from md square after we took this square, after we took from it this square as a common factor? What is left is actually m, and what is left from nd square after we took from it this square as a common factor? What is left is actually n plus, in the next step we take n times n out as a common factor from this expression and also from this expression. So what is left from nm square after we took from it mn as a common factor? What is left? It is actually m plus what is left from mn square after we took from it mn as a common factor? What is left? It is actually n, and it is equals to b square m plus c square n. In the next step, we take m plus n out as a common factor from those two expressions. So what is left from this square times m plus n after we took from it this square, after we took from it m plus n as a common factor? What is left is actually this square. What is left from m plus n times m n after we took from it m plus n as a common factor? What is left? It is actually mn, and it is equal to b square m plus c square n. Actually, m plus n equals to a. It is very easy to see it from the drawing that m plus n equals to a. In the drawing here, according to our definition, side BC of triangle ABC equals to A from one side. But from the other side, side BC equals of course to BD plus DC. BC equals to BD plus DC. So that is to say, BC equals to BD, that is M, plus DC, that is N. Therefore, BC equals to M plus N from one side, from the other side BC equals to A, therefore M plus N equals to A. Okay, M plus N equals to A. So we substitute M plus N in this equation number 3 by A, and we get that M plus N is A, and inside the brackets we have D square plus M times N equals to b square m plus c square n. Okay. And this equation is exactly Stewart's equation. Okay, so proved Stewart's equation according to the first method. In the next step, we'll prove Stewart's equation in the second method. So in the second method, we define angle ADB. This angle is theta. So therefore the adjacent angle ADC must be equal to 180 degrees minus theta. Why? Because this is one side of triangle ABC, therefore it is absolutely a straight line. This is a straight line. So we have rule number 1 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So if you focus on the upper side of the straight line BC at point D, here the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the upper side of BC at point D? We have this angle that is theta plus the missing angle ADC must be equal to 180 degrees according to rule number 1. So therefore the missing angle must be equal to 180 degrees. Why? Because 180 degrees minus theta plus theta equals to 180 degrees, exactly according to rule number 1. Okay, in the next step, we implement the law of cosines on the green triangle. This green triangle, triangle ADB, and then we'll also implement the law of cosines in the pink triangle, triangle ADC. I will remind you what is the law of cosines. The law of cosines is true in any triangle, so this triangle, triangle ABC, could be any triangle. We know that the length of side AB equals to A units, side AC equals to B units in its length, and side BC equals to C units in its length, and this angle BAC equals to theta. Then, according to the law of cosine, the following equation is true that C square equals to A square plus B square minus 2 times A times B times cosine theta. Okay. Then, if we subtract from this equation 2 times AB cosine theta, and then if we add to this equation 2 times AB cosine theta, then we subtract from it C square, and then we divide it by 2 times AB, we will get that cosine theta equals to A square plus B square minus C square over 2 times AB. Okay, so we'll use the law of cosines. So here in this triangle ABC, cosine theta equals to A square plus B square minus C square. over 2 times A times B. Okay, so we implement the law of cosines in the green triangle, ABD. Okay, in the green triangle, ABD, according to the law of cosines, we get that cosine theta equals to d squared plus m squared minus c squared over 2 times d times m. So this equation number 1, is the implementation of the law of cosines in the green triangle ABD. In the next step, we will implement the law of cosines in the pink triangle ADC. So, according to the law of cosines, the pink triangle ADC, cosine 180 degrees minus theta equals to d squared plus n squared minus b squared over 2 times d times n. Okay, here equation number 2 is the implementation of the law of cosines in the pink triangle ADC. Cosine 180 degrees minus theta equals to d squared plus n squared minus b squared over 2 times dn. We have the algebraic identity that states that cosine 180 degrees minus theta equals to minus cosine theta Therefore, according to this trigonometric identity, must cosine in equation number, we substitute cosine 180 degrees minus theta in this equation number 2 by minus cosine theta, and we get that minus cosine theta equals to d squared plus n squared minus b squared over 2 times d times n. So, in the next step, We'll multiply this equation number 1 by minus 1. And we get that according to equation number 1, cosine theta times minus 1 is minus cosine theta. That is equal to, we have to multiply this side also by minus 1, so it is minus. Inside the brackets we will have d squared plus m squared minus c squared over 2 times d times m. So we have two expressions for minus cosine theta. And therefore we create equation number 3 that states that minus cosine theta according to equation number 1 must be equal to minus cosine theta according to equation number 2. So minus cosine theta according to equation number 1 is equal to minus d squared plus m squared minus c squared over 2 times d times m, and it must be equal to minus cosine theta according to equation number 2. Minus cosine theta according to equation number 2 is equal to d squared plus n squared minus b squared over 2 times d times n. In the next step, we'll multiply this equation number 3 by 2d, and we'll get, here in this side of equation number 3 we have 2d over 2d is 1, so 2d will get cancelled, and in the denominator we're left only with m. The numerator didn't change, it's is the same, so it is minus d squared plus m squared minus c squared. Equals to, we have to multiply also this side of equation number 3 by 2d, so 2d over 2d is 1, and in the denominator we left only with n. The numerator didn't change, it remains the same as d squared plus n squared minus b squared in the next step we will first multiply this equation number 3, and we will get that according to equation number 3 minus n, and then here we will open the brackets. Inside the brackets we have d squared plus m squared minus c squared equals to m times d squared plus n squared minus b squared. So in the next step we will open the brackets on both sides of this equation number 3, and we get that according to equation number 3, in this side of equation number 3 we have we have minus n times d is minus n d squared. Then we have minus n times m squared is minus nm squared. And finally, minus n times minus c squared equals to plus nc squared. Why? Because minus times minus is plus. And it is equal to, we open the brackets on this side of equation number 3, and we get that m times d squared equals to md squared plus m times n squared equals to mn squared. M times minus b squared equals to minus mb squared. So actually, this is equation number 3 after we open the brackets on both sides. In the next step, we add to this equation number 3 nd squared. So in this side of equation number 3 we have minus nd squared. So nd squared minus nd squared is 0. And then we will add also nm squared. So in this side of the equation, nm squared minus nm squared is 0. And then we subtract nc squared from this equation number 3. So in this side of equation number 3, nc squared minus nc squared is 0. So in total, in this side of equation number 3, we have 0. In the other side of equation number 3, we have already add this expression, so we copy it as it is, md squared plus mn squared minus mb squared, and we have to add to this side of equation number 3 also nd squared and d squared, and then we have to add to this side of equation number 3 nm squared. And finally, we have to subtract on this side of equation number 3 nc squared. Okay. So in the next step, we take this square out as a common factor from md squared and also nd squared. So according to what we already done in the here before, we have in the first method md squared, we took from it d squared as a common factor, so inside the brackets we left only with m. And we have nd squared, we took d squared as a common factor, so inside the brackets we left only with n, so it is m plus n. Plus we take mn as a common factor, we take out smn as a common factor from this expression and from this expression. So according to what we already done in the first method, here inside the brackets we will have m plus n. And it is equal to nm squared equals to minus mb squared, it is equals to minus mb squared minus nc squared equals to 0, So we add to this equation number 3, mb squared and also nc squared. And we get that only the equation number 3, we have d squared n plus n plus mn plus m plus n equals to mb squared plus nc squared. The next step, we'll take out m plus n as a common factor from those two expressions, exactly as we did in the first method. So inside the brackets we left only with d squared plus m times n. It is equals to b squared m plus c squared n. We have already found out in the first method that m plus n equals to a. Therefore, we substitute m plus n in this equation number 3 by a, and we get that m plus n is a. Inside the brackets we have t squared plus m times n, and it is equal to b squared m plus c squared n, and this is actually Stewart's equation. So we succeeded to prove Stewart's equations in two different methods. In the next step, I'll summarize the lecture. We start with the first method. In this lecture we proved Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides in the triangle to the length of its CVN. The CVN here is AD, and the CVN AD equals to the units in length. The length of side AB is C units, the length of side AC is B units, and finally the length of side BC is M and A units, and line segment BD equals to M units, and line segment DC equals to N units in its length. So I repeat again, Stewart's theorem yields a relation between the lengths of the sides in the triangle to the length of its CVN. The length of the CVN AD equals to 3 units in its length. And according to Stewart's theorem, b squared times m plus c squared times n equals to a, and we open the brackets. Inside the brackets we have d squared plus m times n. Again, b squared m plus c squared n equals to a. We open the brackets. Inside the brackets we have d squared plus m times n. So we proved that this equation is true in two different methods. In the first method, we did a construction that is to say, from point A we draw perpendicular on BC. So therefore this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC is E. We define the length of line segment ED. This line segment ED is X. We define the length of line segment AE is H. And here line segment EC equals to X plus N units in itself. And line segment BE equals to BD, that is M, minus ED, that is X. Total line segment BE equals to M minus X units in itself. Okay? Then implemented the Pythagoras theorem on the green right triangle AED. According to the Pythagoras theorem on the green right triangle AED, AD square equals to AE square plus ED square. Repeat again, the right green triangle AED, AD square equals to AE square plus ED square. Okay. Here AD equals to D, AE equals to H, and ED equals to X. Therefore, according to the Pythagoras theorem, this square equals to H square plus X square. Okay, we substitute AD by D, we substitute AE by H, and we substitute ED by X. And we got that this square equals to H square plus X square. Then we implemented the Pythagoras theorem on the right triangle, triangle AEC. In the right triangle, triangle AEC, according to the Pythagoras theorem, AC square equals to AE square plus EC square. Repeat again. Triangle AC, according to the Pythagoras theorem, AC square equals to AE square plus EC square. AC is B, AC equals to B units in its length, therefore AC square is B square, AE is H, therefore E square is H square, AE square is H square, and finally here EC equals to X percent, therefore EC square is X percent square. So in conclusion, found out that according to equation number 1, B square equals to H square plus X plus N square. In the next step, we open the brackets of this side of equation number 1, and we found out that according to equation number 1, B square equals to H square plus X percent square equals to X square plus N square plus 2 times Xn. This is equation number 1. We have here H square plus X square, and we already found out that H square plus X square equals to D square. So we substituted X square plus X square by D square in this equation number 1, and we found out that according to equation number 1, B square equals to H square plus X square, that is D square, plus N square plus 2 times X times N. Then we created equation number 3 by implementing the Pythagoras theorem on the right plane triangle AEB. In the right plane triangle AEB, AB square equals to AE square plus EB square. Repeat again, the right plane triangle AB square equals to A square plus BE square. The hypotenuse AB equals to C, therefore the square of the hypotenuse is C square. AE equals to H, therefore A square is H square. AE square is H square, and finally BE equals to M minus X, therefore b squared is m minus x squared. So in conclusion, we found out that according to the Pythagoras theorem, in the right pin triangle ABC squared equals to a squared plus m minus x squared. We open the brackets of this side of equation, on this side of equation number 3, and found out that according to equation number 2, and found out that according to equation number 2, c squared equals to a squared plus m minus x squared. M minus x squared equals to m squared plus x squared minus 2 times mx. And we have here h squared plus x squared equals to d squared. Therefore, we substitute h squared plus x squared in this equation number 2 by d squared. And we found out that c squared equals to h squared plus d squared is this, h squared plus x squared is d squared plus m squared minus 2 times mx. So we have here two equations, equation number 1 and equation number 2. In the next step, we created equation number 3 in the following way. First of all, we multiplied equation number 1 by n. In the second step, we multiplied equation number 2 by n, and then we added the two equations with each other. This created equation number 3. We did the process in two steps. In the first step, we multiplied the right side of equation number 1 by m. This is the right side. So it is m, inside the brackets we have d squared plus n squared plus 2 times xn. In the second step, we multiplied the right side of equation number 2 by n. This is the right side of equation number 2, so it is n times, inside the brackets we have d squared plus m squared plus 2 times mx, and we added the two sides with each other. So this side equals to the right side of the equation equals to the left side of the equation. So, and it must be equal to the multiplication of the right side or the left side of equation number 1 by m. So it is in the right side, in the left side of equation number 1 we have b squared. So it will be mb squared plus the multiplication of the left side of equation number 2 by n. In the left side of equation number 2 we have c squared, so it is nc squared. Okay, in the next step we open the brackets of this side of equation number 3. So here we have m times b squared is mb squared, m times n squared is mn squared, and m times 2xn is 2xmn. We open also the brackets of this expression. So we have here n times d squared is nd squared, n times m squared is nm squared, and n times minus 2mx is minus 2xmn. And it is equal to mb squared plus nc squared. So in this side of equation number 3, 2xmn minus 2xmn is 0. So those two expressions will get cancelled, and after we cancel the two expressions, we left what is left from equation number 3 is this expression, mb squared plus mn squared plus nd squared plus nm squared equals to mb squared plus nc squared. In the next step, we took out d squared as a current factor from md squared and also from nd squared, so inside the brackets we left only with m plus n. Then we took out m times n as a common factor from this expression and from this expression, and therefore inside the brackets we left only with m plus n. And it is equal to b squared m plus c squared n. In the next step, we took out m plus n as a common factor from those two expressions, so inside the brackets we left only with d squared plus mn, and it is equal to b squared m plus c squared n. And I've already showed you that m plus n equals to a. From the drawings it's very easy to see that from one side BC equals to m plus n, from the other side BC equals to a, therefore m plus n equals to a. Therefore we substituted m plus n in this equation, equation number 3 by a, and we got that m plus n is a. Inside the brackets we have d squared plus mn, and it is equals to b squared m plus c squared n, and this is exactly Stewart's theorem. Then we proved Stewart's theorem in the second method. In the second method, we defined angle ADB as theta. Therefore, the adjacent angle ADC must be equal to 180 degrees minus theta, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. Okay. Then we implemented the law of cosines in the main triangle ADB. What is the law of cosines? The law of cosines is true in any triangle. So this triangle ABC, could be any triangle. We know that the length of side AB is A units, side AC equals to B units in its length, and finally side BC equals to C units in its length, and angle BAC equals to theta. Then according to the law of cosines, the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Then it is very easy to arrive from this equation to this equation. So we found out that cosine theta, according to the law of cosines, equals to A squared plus B squared minus C squared over 2 times A times B. So we implemented the law of cosines in the great triangle ADB. According to the law of cosines, in the great triangle ADB, cosine theta equals to d squared plus m squared minus c squared over 2 times d times m. I'll repeat again, in the great triangle ADB, cosine theta equals to d squared plus m squared minus c squared over 2 times d times m. Then we implemented the same law, the law of cosines, in the pink triangle ADC. According to the law of cosines in the pink triangle ADC, cosine 180 degrees minus theta equals to d squared plus n squared minus b squared over 2 times d times n. Repeat again, the pink triangle ADC, according to the law of cosines, cosine 180 degrees minus theta equals to d squared plus n squared minus b squared over 2 times d times n. Then we have the trigonometric identity that states that cosine 180 degrees minus theta equals to minus cosine theta. So we substitute cosine 180 degrees minus theta in this equation number 2 by minus cosine theta. So it is equal to d squared plus n squared minus b squared over 2 times d times n. Then we multiply this equation number 1 by minus 1. So minus 1 times minus cosine theta equals to minus cosine theta, and we multiplied also this side of the equation by minus 1, so it is minus, inside the brackets we have d squared plus m squared minus c squared over 2 times d times n. Then we have two different expressions for minus cosine theta. Therefore we created equation number 3 that states that minus cosine theta according to equation number 1 must be equal to minus cosine theta according to equation number 2. Minus cosine theta according to equation number 1 equals to d squared plus m squared minus c squared over 2 times d times m. And it must be equal to minus cosine theta according to equation number 2, and minus cosine theta according to equation number 2 equals to d squared plus n squared minus b squared over 2 times d times n. Then we multiply this equation number 3 by 2d. So on this side of equation number 3 we have 2d over 2d is 1, so 2d will get cancelled. So in the denominator of this side of equation number 3 we left only with m. The numerator didn't change. It remains as minus d squared plus m squared minus c squared. Then we multiply this side of equation number 3 by 2d. So here 2d over 2d is 1, so in the denominator we left only with n. The numerator didn't change. It remains d squared plus n squared minus b squared. Then we cross multiply this equation number 3, and we found out that according to equation number 3, minus n d squared, inside the brackets we have d squared plus m squared minus c squared, and here m times d squared plus n squared minus b squared. Then we open the brackets on both sides of this equation number 3, and we found out that according to equation number 3, in this side of equation number 3 we have minus n times d squared is minus n d squared, minus m times m squared is minus n m squared, and finally minus n times minus c squared is plus n c squared. Then we opened the brackets on this side of equation number 3 and found out that m times d squared is md squared, m times n squared is mn squared, and finally m times minus b squared is minus mb squared. So actually, this is equation number 3. After we open the brackets on both sides, in the next step, we added to this equation number 3, nd squared. So here we have nd squared minus nd squared is 0. Then we added m squared. So here nm squared minus nm squared is 0. And finally we subtracted from this equation number 3 nc squared. So nc squared minus nc squared is 0. So in this side of equation number 3 we left with 0. Okay, and then we have to do the same operation in the other side of equation number 3, of course. So in this side of equation number 3 we have already had the expression of mb squared plus nm squared minus mb squared, and we have to add to this equation number 3 nd squared, and we also have to add of this side of equation number 3 mn squared, and we have to subtract from this side of equation number 3 nc squared. Okay. Then we took out this square as a common factor from this expression and from this expression, from md squared and also from nd squared. So inside the brackets we left only with m plus n. Then we took mn out as a common factor from those two expressions. So inside the brackets we left only with m plus n, and we have also here minus mb squared minus nc squared equals to 0. The next step we added to this equation number 3 nd squared plus nc squared. So on one side of the equation, because we have 0, so after we added nb squared plus mc squared, the 0 that equals to this side that equals to 0, it will be equal to mb squared plus nc squared. On this side of the equation number 3 we have this square times n plus mn times m plus n. In the next step we took out m plus n as a common factor out of those two expressions. So inside the brackets we left only with d square plus mn, and it is equal to b square n plus c square n. We have already found out that it is very easy to see from the domain that m plus n equals to a. So we substituted m plus n this equation number 3 by a, and found out that here m plus n is a. Inside the brackets we have d square plus mn, and it is equals to b square n plus c square n. And this is exactly Stewart's equation. So we succeeded to prove Stewart's equation in two different methods. Okay, thank you very much.